Okay, I think we can start now, and there'll be probably a few others that might come in. And I'm Barry Goodison. I'm currently chair of the CMOS Ottawa Centre, and I'd like to welcome you to our virtual lunch and talk that we have usually on a monthly basis, and welcome people from across Canada that may have joined us, been able to join us today. It's great. A couple of housekeeping notes first, as Denis just mentioned about turning off your video and your audio. That would be extremely helpful. Any of you that have been on these talks before realize that we generally handle the questions through the chat function. So you can type your question at any time into the chat function. And Helen Joseph is our moderator today, who will bundle those questions and feed them to our speaker at the end of the talk. As you may have noted on the way in, this talk is being recorded, and it'll be available on the CMOS YouTube channel in the near future, usually within 2 to 3 days. So it's with great pleasure that I'd like to introduce our speaker today, Dr. Stephan Gruber from Carleton University. He joined Carleton in 2013 as a Canada Research Chair in Climate Change Impacts Adaptation in Northern Canada. And as you might have noticed, he's started his career in Europe, in Switzerland, and with University of Zurich. But he's also had periods where he's been able to work in other countries, other situations, did Arctic studies in Finland. And he brings the perspective of not only in the context of permafrost to high latitudes, such as the Arctic, but also to high altitudes, where a lot of his work was done initially. He's been involved in IPCC, a special report on ocean and cryosphere and the changing climate, but has also been involved in summary for the policymakers in that. But he's also had experience in the past in the Himalayan region, and he was a co-editor in chief for the online journal called the Cryosphere, which has become really important. But I think one of the key things, or it is one of the key things that he's been involved in, is leading the NSERC Permafrost Network. It's a partnership network across Canada, involves 11 institutions, and a lot of it is aimed at understanding the interactions between climate, permafrost, and infrastructure. And some of his focuses raises the question of, can you move into operational services in the context of permafrost? So I hope today's meeting, entitled Toward Permafrost Climate Services, will shed some light on that aspect. And I welcome Stephan, and please take over.
Thank you, Barry, for introducing me. And let's see if I can share my screen. Does that work?
Yes, you are sharing well.
Excellent. So in this image, you see permafrost research at one time and at one location in Canada. A number of people downloading temperature data loggers that are somewhere in the ground here that can't be seen remotely. And that happened this summer in an exploration camp at the Tundra Taiga Transition in Northwest Territories. In the background are some muskox watching this. You know, it was all very nice. It's also all very expensive. Why are we doing this? You know, about half of Canada's exposed landmass is underlain by permafrost, and most of that will undergo pervasive and persistent thaw under anthropogenic climate change. Persistent means that progressively thawing ground will cause changes for decades and for centuries. And this will affect Northerners strongly, and also it will affect all Canadians. And this is going to be, for example, via national identity. The true North is changing and becoming a new North. It will affect national defense, disaster response, sovereignty, and it will require increasing amounts of money to keep certain parts of the country accessible and to give residents their access to the services they deserve. And so permafrost thaw is a known unknown, and it's affecting the country. But to bring these two statements now, the fieldwork and the bigger picture for the country together, we can ask, how is the research of my students and the research I perform going to help Canadians respond to and adapt to climate change? And I think here it's helpful to recognize that the issue, of course, is broader than permafrost and broader than Canada alone. And a special report on the ocean and cryosphere and the changing climate, SROCC, reveals that the benefits of ambitious mitigation and effective adaptation, and conversely, the escalating costs and risks of delayed action. So these are statements from the summary for policymakers. So I assume we all want to contribute to not delaying action and to supporting effective adaptation. But how do we best do that in the context of permafrost? And in this talk, I want to explore how operational services for permafrost might fill a critical gap in enabling adaptation to future permafrost thaw, and then in the end, show you a few examples of research going into that direction. So if we look at the SROCC summary for policymakers, then I've drawn out a few statements here, slightly modified or shortened. Essentially, the challenges revolve around widespread thaw, changing hazards, and a reduced effectiveness, of the methods we have for reducing risk and losses. If we look at what it takes to implement responses, there are a few considerations here. They strongly involve around people. I briefly want to explain a bit further the first statement that says people with the highest exposure and vulnerability to current and future hazards are often also those with lowest adaptive capacity. This refers both to residents of the Arctic, residents of high mountain regions. And the lowest adaptive capacity, of course, doesn't refer to intrinsic properties. This is not degrading people and saying you don't have this capacity. It's actually quite the opposite. Often people living in the Arctic or in mountain environments have a long tradition of being able to adapt very well to changing environmental conditions. But how they're being supported by societies at large, how they have access to resources to adapt, is often not the same as what people would have in urban centers. So all of this is to say that the issue really transcends national borders, and it also transcends differing parts of the cryosphere and the climate system. And I wouldn't be a proper academic if I wouldn't give you some definition somewhere that I often find dreadful when I see it, but maybe because this is not the permafrost crowd, it's good nevertheless. So permafrost is ground, and in this are included soil, rock, ice, organic material that remains at or below 2 degrees Celsius for at least 2 consecutive years. And we have this definition because temperature is easy to measure. But we're actually interested in whether there is ice in the ground, whether that ice has been there for a long time. Because when that ice thaws, that ice melts, things change. And so when we speak of permafrost thaw, we usually mean the progressive loss of ground ice in permafrost. And that could lose a proportion of the ice that's in a certain volume of soil, or it could lose all of the ice. And this ice loss, of course, brings about physical change. You see this little round blob here in the middle. That's the IPA map, the map that was put together by the International Permafrost Association. And that for the first time has really shown people, has shown laypersons how much permafrost there really is. It's about 1/8 of Earth's exposed land area has permafrost in the subsurface. But unlike glaciers and ice sheets and snow, we can't fly a satellite and easily say, look, this is what permafrost is and this is how it behaves. And because it's so difficult to observe, it often escapes our perception. And on the right-hand side is just a little reminder, permafrost occurs in mountain areas and in polar areas, and it's also a bit of an introduction to myself. The image above is, my graduate students working with me 10 years ago, and the image below is today. The hazards used to be gravity and rockfall, and now it's mostly mosquitoes and bears. So how do we inform adaptation and mitigation? Well, we have to ask ourselves what decisions are involved in addressing challenges of permafrost thaw and who makes these decisions, and what knowledge or data is needed to inform these decisions. Who holds or can produce this knowledge, and what forms of delivery are appropriate for the intended users. And some of these questions are important and difficult to answer because permafrost, as I've just said, isn't directly visible, and it may not actually be on the minds of the knowledge users, because so far the changes that will plague their future lives haven't fully occurred, or maybe they have occurred depending on where you are on the planet, but they haven't been brought into connection with permafrost yet. Now, climate services, in my opinion, are a very useful framing for this, because the concept has created a lot of experience already and a lot of insight over several years now. It's focused on decisions and on co-development or co-production. And there's also experience with this in other fields that include public service administration, science policy, science and technology studies, participatory development, research with indigenous peoples. And it's very nice that this is fundamentally baked into the framing of climate services. And the diagram here on the right, taken from the global framework for climate services, it looks like it requires large organizations, but it also emphasizes different elements that need to work together. And then there's this umbrella, in a way, of capacity building that occurs within and between all the other components. And what we also see here is that the scope of users is deliberately kept very broad. A lot of times as scientists, we tend to be biased in producing our products only for other scientists to consume. But there's a whole host of other people who would actually be involved in, creating value with the research results we produce. I think if we were to, think about permafrost climate services, they will have a number of distinct attributes. For example, their history. We would just be starting now to think about this. The climate services that we usually speak about, they evolved from, for example, national weather services. And they, of course, had their own period of growth and their own learning there. But if we develop permafrost climate services, we're starting from scratch in most countries. Nothing like that really exists. And there isn't an awareness that there is a cost that is worth incurring, right? If we fly a jet from Ottawa to Calgary, then there is a meteo station at both airports, and people to tend to this meteo station. There's numerical weather prediction, and these numerical weather prediction products are delivered not only on my iPhone, but they're also delivered for the flight weather and the flight planning. If we look at how this works for permafrost, if there is something you need to know, you commission a graduate student to do something, or an engineering company. And we're not commissioning graduate students to making the flight weather forecasts for, Air Canada. And so we're really starting there from something where we're not used to having services. Perception is something. Permafrost areas are often in the periphery, and the hazards that occur there affect few people directly, and sometimes in unusual ways, because we might be focused on the cost of damage to large infrastructure, whereas people living in mountains or people living in the north, they might have their livelihoods or their traditional livelihoods transformed by, I don't know, traditional berry patches, transforming into wetlands or lakes draining catastrophically. And we're not always really set up well to having these things transported into our perception the same way as we would, for a large earthquake. And then there's, processes and perceptions. We're really interfacing, and I'm going to hammer home this point. We're interfacing a community that deals with the atmosphere and with modeling and with time series, and a community that deals with the subsurface, with static maps and with boreholes, geology and geotechnics. Let's look at this in a little bit more detail. I've been conceptualizing this a little bit as a Venn diagram, as you see it here, where we can think, okay, so let's think about three overlapping domains: infrastructure and land use, and this could also be traditional land use, the terrestrial environment, and climate events or trends. And if we start looking at the only overlaps between two of those, then of course, if there are changes that occur in the natural environment without effects on infrastructure and land use, then they're not really all that relevant if we think about services that support decision making. The intersection between infrastructure and land use with the terrestrial environment, of course, there's a well-established long practice of mapping, recognizing, delineating, assessing, dealing with hazards in stable climate. This is established practice. There are standards for this. People study this in universities. Similarly, where infrastructure and land use overlap with climate events or trends, there is a whole host of services and expertise available to think about what atmospheric hydrologic hazards occur in stable climate. This is established practice, and climate services, I would say, are the emerging practice of dealing with this under climate change. Somewhere in the middle here, of course, people always put their slides together in a way that their own domain is in the middle and very central, and I've done that here too. This is hazards in permafrost areas under climate change. So here we have an overlapping of these three domains, and that in essence, brings something new for us to accomplish. And different communities need to come together to form this new practice. And the word geology that I've inserted here is just a shorthand to describe superficial geology, quaternary geology, geomorphology, and geotechnical engineering, who have so far developed the techniques that allow us to understand permafrost sufficiently well to deal with it under stable climate conditions. Just to drive this home a little bit more, I've inserted a little permafrost core here on the right. You see alternating layers of frozen silt and clear segregated ice. And then I've just indicated that more on one side we have atmospheric sciences. There's more modeling, more time series. There's more of a tradition to monitor, to provide services with monitoring data and time series. And then geological sciences that are more focused on drilling and on mapping, that don't usually have time series as much in their everyday business. So let's look at a few services that are emerging already today. So there are international efforts, the Global Terrestrial Network for Permafrost, GTNP, and Permafrost CCI, that's Climate Change Initiative. This is a large ESA, European Space Agency program. They're both aligned with WMO and climate monitoring. They're sustained over many years, although often with very thin resources, especially the Global Terrestrial Network for Permafrost. The data are openly available, and my interpretation of what I see here is that scientists are intended as primary users, right? This is going to inform, for example, international assessment reports. These products are focused mostly on temperature, not directly geology or ice loss. It doesn't really speak to thaw. And as a side note, the GTNP used to be led by Canada and was hosted in Canada, but I think did not have adequate funding. So now this is largely supported and run from Europe, mostly Germany. I think Canada has a future opportunity here to, fully fill its role of Arctic leadership in this regard. If we look at Switzerland, it has the Swiss Permafrost monitoring system PERMOS, and during and after my PhD, I kind of grew up in this crowd and being part of PERMOS. So this has influenced a lot of my thinking, and PERMOS actually was strongly informed by the World Glacier Monitoring Service that was hosted at the same institution. PERMOS is focused on monitoring and observations, has a 20-year, bit longer actually now, tradition, has stable staffing in a federal department. It has governance and a stable mandate. The data are openly available. They contribute to international monitoring initiatives. And they also provide the Swiss Permafrost Bulletin with very nice interpretation and context that is suitable for non-specialist audiences. And I think this is a very nice example of getting something like this going. And then Canada has a lot to offer that now starts to become more visible. There are several databases and portals that are emerging now by federal and territorial geological surveys, often focused on geotechnical data, the very data that tells us, where is the ice in the ground, some temperature data. The Canadian Centre for Climate Services has northern liaison officers. So it has a strong view already towards serving the north of Canada, and it has a Northern Data Working Group that is also currently thinking about some of the issues that I'm presenting here. And then we have NSERC PermafrostNet. I'll speak about this a little bit more in a bit. That's a project that aims at prototyping permafrost climate services and data interoperability. And we're also in the process of leading or catalyzing a national strategy exercise on permafrost and, research and services, how that could help Canadians. So there's a lot ongoing currently in this space. And so essentially, again, thinking about permafrost thaw, adapting to permafrost thaw in the future, I think what we want to do is to go from best practice to next practice, where best practice basically means knowing that permafrost exists somewhere, maybe figuring out its characteristics at one area with drilling and site-specific studies, and then avoiding disturbances that we might cause with a building or something like that. And the next practice would be taking a forward-looking approach to hazards that occur from transient thaw and considering climate-driven thaw and disturbance. And for this, we need new types of expertise and new combinations of expertise. Permafrost climate services, I believe, are able to inform and underpin this practice. We have to ask ourselves, is academic research best positioned to produce and deliver these kinds of data and products that we need? And I think, well, there's a prominent role in developing and prototyping permafrost climate services, but unless there's something stable to provide those services to the people who need them, I don't think we're really rising to our full potential with what we do. And this is kind of encapsulated in this little drawing here on the right. I guess this is the traditional risk equation where you have hazards and exposure and vulnerability multiplied to provide risk. We have permafrost thaw that affects hazards, and permafrost thaw itself is driven by climate change and affected by development. And the best way for us to do something there with adaptation is to affect adaptation via next practices, and underpinning these would be knowledge products that would be delivered as permafrost climate services. So this diagram here is taken from the proposal of NSERC PermafrostNet, that is an NSERC strategic partnership network funded for 2019 to 2024 I believe we will be getting an extra year at no cost extension due to COVID. It connects 40 different partner organizations that really span all different levels of government, indigenous organizations, private companies, 39 graduate students and postdocs, 15 different investigators. Those are the funded professors, and 30 collaborators. These are researchers participating from the partner organizations. And the overall goal of this is to boost Canada's ability to adapt to permafrost thaw. And this network came out of a workshop that we held in Ottawa in 2017. And so the community there got together and recognized that, there's a need to get networked better to approach bigger research questions and to approach questions that drive towards products that can help stakeholders. What also came out of this 2017 workshop, by the way, was the Canadian Permafrost Association. That is an association that represents permafrost research and practice in Canada broadly. It's open to anyone, whereas of course in NSERC strategic network, we need to select who's part of the proposal. And I think this gave a lot of momentum to the community organizing going forward. Oh, and by the way, PermafrostNet, has a shareholder, not shareholder, a stakeholder-led governance, with people from all different sectors participating in this. Now, in NSERC PermafrostNet, we have 5 different themes. So one focuses on characterization of permafrost, one is monitoring, one is prediction, we have hazards and adaptation. And it's quite a lot of people that need to be coordinated here. And despite COVID, all the themes have started, most of the students have been recruited, all the research has started. And so now slowly the network research is emerging, and I've just inserted a few additional things here. One is just, we made this little network graph here for the proposal where you see just how individual people interact just through the thesis committees of the students. And some of these interactions are what I hope and I believe is going to strengthen this increased connectivity with research and stakeholders, but also between atmospheric science and the more geologically minded people. But of course, each of these nodes in this network is a person, and each of the edges in this network is an interaction that needs time and an effort, and is essentially an activation energy that individuals invest in transforming the community. Now, these are the outputs, network level, that the network aspires to, a synthesis reporting on how is permafrost doing in Canada, data products, and these will be essentially climate service prototypes, many of them, and then next practice. If we look at the expected outcomes for the network, then there's improved understanding, methods to dealing with permafrost thaw, new experts that get educated, and a new community that emerges from this. Somewhere in between this, of course, between next practice and these outcomes, is a vision and a strategy. So how do we want to evolve as permafrost research community in Canada? How do we make sure that this is not lost effort? And so the network will be also a catalyst for an open and inclusive strategy and visioning exercise. It will include key government players, Northerners, the Canadian Permafrost Association, and so on. And I want to invite you to contact me if you want to contribute to shaping this strategy and vision. We really want to have everyone on board in this. So with all of this high-level stuff, let's get a little bit closer into looking at permafrost and how we can model it, just to get a little bit closer to the frozen dirt. When we simulate permafrost thaw, then this is essentially something that has both the subsurface and the atmosphere surface energy balance in it. And in these plots here, these are just examples. You see, these are both time series. There's time on the horizontal axis, and we have depth on the vertical axis. And then you can see that this particular model output, in the top one, we have temperature given for a color scale. The bottom one has liquid water content given as a color scale. And you could, of course, also think about this as being an ice content. There are other variables that we can show. And you see that, the model simulates, the buildup and decay of a snow cover, the heat transfer in the ground. You see the red line here and here. This is the thawing of the ground in summer. You see a purged water table on here. And so, they're essentially like the land surface models that need to have some extra capabilities to deal well with the ground thermal regime, a snowpack, and phase change in the ground that isn't always as trivial as it seems. Now, when we want to model phase change in the soil, then I'm just showing you this little permafrost core here, where we have alternating layers of frozen soil, shown with the orange dots, and then in between are these layers of pretty clear segregated ice. And when we have water in porous media, then the water, if you look at one of those dotted lines here that have the orange dot, this is temperature here, by the way, and this is the proportion of the water that is liquid or frozen. Then the water in this porous medium doesn't freeze at exactly 0 degrees Celsius, but it progressively freezes or progressively thaws over a long, wide temperature range. But when we have relatively pure ice, this, what we call a freezing characteristic curve for water, is extremely steep. There's just like a little zoom in here for linearization that we use in one model. So these two different parts in the soil, actually almost clear ice in the soil, they need different ways of being treated, because the ice in the orange bit of the soil here is going to thaw already before we reach 0 degrees Celsius. The clear ice here, however, thaws much later. This very steep enthalpy function makes numerics often difficult. It's very difficult to spin up deep soil profiles, right? Many land surface models have soil profiles that are, say, only 3, 4, 5 meters deep. They're easy to spin up. But once you're 100 meters deep, as often you need for permafrost, spin up until your temperature profile is in equilibrium with your surface energy balance takes a very long time. Now imagine you have latent heat in the soil. This will mean that your temperature is going to stay close to 0 degrees during heat transfer. So you have a very low temperature gradient to remove a lot of heat. So spin up around 0 degrees Celsius can easily take a very long time. The other thing to realize here is that the initial content of excess ice, right? If we don't know how much ice is in the soil to start with, how can we figure out anything about impacts of climate change? So this is a key determinant of impacts. It's highly variable in space. It's expensive to measure. Data we have are sparse and biased, and it can't be easily modeled. We can't just spin up the evolution of the landscape in these models. Another issue, of course, is that many models we use today have a fixed geometry, whereas if we do have excess ice, we are faced with subsidence. Just as a little sketch here, this is forcing at a surface for a soil column. Thaw penetration means how deeply into the soil is a thaw front penetrating. And the abbreviation EI here means excess ice. So if we don't have excess ice, there's a certain amount of thaw penetration. Here it's a bit more than a meter. The sum of thaw progresses into the ground, and then the ground refreezes. If there is excess ice, this is less, because excess ice, that is the amount of ice that's in excess of the consolidated thawed pore space. After that ice melts, the water just runs off to the side and the soil consolidates. And this consolidation is what we see here. That's this difference here. And so the moment we want to deal with this, we need to have a little bit more advanced models than we often use for the land surface. And then, of course, this affects water transport, surface ponding, and so on. So the take-home message here is that simulating permafrost thaw is not all that easy, and we need to know how much ice is in the ground to start with. I want to give you a quick example of a study done close to the Ekati and Diavik diamond mines. Just show you a few examples of ice in the ground. And the images here on the right just show you how expensive it is to get these cores. So you need to have a helicopter transported drill rig in the summer, or something that is dragged in large sheds in winter with heavy equipment. So what we found, interestingly, what we call upland till. So this is a little hill that's 10 or 15 meters higher than the surroundings. Here's the borehole where we also measure temperature. And on the right, you see the cores of frozen soil that we recovered. And we interpret this to be remnant basal ice from the Laurentide ice sheet preserved under permafrost conditions, with about 40 to 45% excess ice. So the soil would consolidate significantly. The fact that it derives from a Laurentide ice sheet already tells us that this is something that needs to have a long-term view if we want to understand where the ice is and where the ice isn't. If we just move a couple hundred meters away from that space that I've just shown to one of the more low-lying places, then we find different types of ice. And beneath that, we also find the old till that has already once thawed out. And difference is caused not only by basal conditions underneath the Laurentide ice sheet, but it's overprinted what happened during the Holocene in terms of climate changes and vegetation changes that in the depressions caused permafrost to thaw out. And so take-home message here is that estimating the initial ice content in the ground will need to rely heavily on geologic methods and data. And it's going to be difficult to bring this into the world of transient modeling and to figure out how we deal with this degree of uncertainty and spatial variation. The same is true, by the way, in terms of spatial variation for temperature, right? If we measure temperatures in the ground there and we have a couple hundred instruments, then it differs on the annual mean by almost 10 degrees laterally. It's almost as much as the difference in mean annual air temperature from Yellowknife to Ottawa. To drive home the importance of spatial variation, I want to show you this picture that I used to use a lot when I lived in Switzerland. And what it shows here is this yellow plane that a couple years ago would have been a high-resolution regional climate model cell hovering at average elevation on a part of Switzerland. Now, a permafrost model, a snow model, a land surface model would be evaluated once for this yellow surface, right? Well, whatever the result is from there, how is it going to inform someone down here in the valley who grows wine for a living? And how is it going to inform someone who runs a train station up there in permafrost at 3,500 meters? The answer is it doesn't really do that well. It's also very difficult to test this model with observations. So the take home here very quickly is that permafrost climate services would need to be delivered at an appropriate scale, right? Kind of a plot scale that you can compare to measurements at the scale at which actually ice is lost in permafrost. So thinking about how we would make these simulations and looking at a map of Canada or the Arctic in general or mountain regions outside Switzerland, it's very difficult to drive models at the places where we need them, where we have data to test models or where we need the models for predictions. The take home here is that we likely need to rely on reanalyses for comparing model and observations, because if we don't have the ability to produce model simulations where we have our observations and where we need the outputs, then we can't really make progress. It also tells us that we need to look at error and uncertainty carefully if we want to work with this, because these sparse stations in the north also put new and different question marks, possibly on global data products. So over the past few years, we've developed a pretty nice code base for using ensembles of reanalyses for driving permafrost simulations at the plot scale, pretty much anywhere where we like. And we've done this with data measured in those remote places where I've just shown you the boreholes with the ice. And what you see here on the left, this lower diagram here shows what we call the surface offset. And essentially it says the mean annual ground temperature. How much higher is it than the mean annual air temperature, right? It's a very nice measure for us to understand what is the local variation in ground temperature that's caused by topography, water, snow, and other things that happen at ground level. And what you see here, this histogram, blue and red, there are different years measured. But what you see is there's about a 10-degree differentiation laterally over distances of a couple 10 or a couple 100 meters. And what you see on the right-hand side here are different groups of these locations that we have simulated with the Permafrost model that we use, driven by ERA interim and observed in the field. And what you see from this is that we kind of reproduce actually the seasonal evolution of the temperatures reasonably well. And if you look at the top here, then it kind of shows the observed surface offset and the modeled surface offset clustered by these different surface types. All that is to say, as a take-home message, simulating ground temperature at the plot scale based on reanalysis is promising as something that we can take forward. And the next steps really in this, and this is something we're doing in NSERC PermafrostNet, would be to test the modeling chains with observations now that we can both connect them at the right place, to begin driving models with CMIP6 scenarios debiased with reanalyses, and start incorporating estimates of subsurface ice content in ensembles of permafrost change and impacts of permafrost change that we calculate. And some of my students are also doing this at the moment. I want to finish with a few key messages, and in this, I think the first one is to say permafrost thaw is the known unknown, especially for Canada, and there isn't really an excuse for not being prepared what is going to come, and what's already there in many ways. Permafrost services enable adaptation to permafrost change, and framing them as climate services is great because it allows us to draw on what we've learned already about co-production, and it allows us to focus on informing decisions and not just focus on what I like as a scientist. I think these services will gain importance in a lot of countries and internationally, and Canada really has a good chance here to become a leader and maybe an obligation to become a leader. The services that I talk about here will not only be good for stakeholders and for adaptation, but they will also be supercharging in a way basic research about permafrost and basic research about permafrost carbon feedback and so on, because often it's those services that help us then to address research questions that we couldn't before, because a group of graduate students just can't generate the same data as a stable center can. And maybe last but not least, there is a lot of fast progress that's being made right now scientifically in terms of technology for providing simulations, but also organizationally, how we deal with this in Canada and how we come together with different communities. With that, thank you very much, and I look forward to the questions you might have.
Thank you very much, Stephan. You've covered a lot of territory. It's a great overview, introduction on permafrost. As you said, a non-permafrost crowd for the most part. So it's Helen here, and I'll look forward to fielding the questions for you. I'll try to. I'll read them from the chat. If folks and participants today aren't familiar, what we generally do is please put your questions into the chat. I see Bill Pugsley has got there already, but please put your questions in the chat and I'll read them and just moderate the questions. So first question, as I say, is from Bill, and his question is, what connections and potentials are there between permafrost and permafrost thawing and geothermal heating, particularly populated areas in the Arctic such as Yellowknife, Fort Smith, and Inuvik?
I would have to pull this out of my nose because I haven't really looked at this. My intuitive response would be that if it's like shallow geothermal heating, where you you have a heat pump operating, it might actually be interesting in winter when but otherwise, I don't know how that would affect geothermal heating.
Okay, thanks, Stephan. You froze there for just about 2 seconds, but it looks like you're back. So we'll hope, keep fingers crossed this holds for another little bit. Okay, a couple more questions popped in there. One from Barry, that would be Barry Goodison. Can you expand on your thoughts that Canada can become a leader? The who, how, etc., and what kind of feedback have you had from departments such as Environment, Climate Change Canada and Natural Resources Canada?
We've had conversations with both organizations, of course, and both are in contact with us for thinking about developing such a strategy or vision, because ultimately I think it will be up to the government to pick this up and implement it. I think the response we've had, the responses are enthusiastic. But even this question kind of shows one of the problems, right? This is distributed over different departments, and how is this going to work? The chances I think Canada has as a leader are, in my mind, doing what's needed for Canada and including the rest of the world after that. That's just an incremental step, right? If you think about managing Canada's permafrost data properly, then also to include the rest of the world is going to be a small incremental step with the benefit of being able to learn from all the other data. I think there's going to be a lot of benefit in this. And I think even just the thought of permafrost climate services would be something that is at the core of what Canada could be about in terms of Arctic and climate change. So I think there are a lot of possibilities.
Great, yeah, thanks, Stephan. David Fisher has a question up here next. He's asking, I think he wants to go back and look at one of the slides maybe. Could you show the seasonal GST simulations again? He was asking, it was hard to see the x-axis.
Yeah, this is what's up here. The x-axis are months. So x-axis is time.
Okay.
So it's September, November, January, and so on.
Good. Thanks for that clarification, Ben. Next question is from Jim Abraham, joining us from the East Coast. Are there any ways that permafrost can be measured using a volunteer citizen science program?
I'm actually sure that there are going to be many ways to do that. There is a little obstacle, of course, and that is that if we walk around in the landscape during summer, we have the so-called active layer that develops. That's the topmost layer where the soil thaws annually over permafrost. So before we reach the actual permafrost, we need to dig or drill a little bit. But there are a lot of useful things to monitor. And I also think that programs for community monitoring with respect to standardized equipment, even for monitoring temperature, for monitoring snow height, for monitoring subsidence, would be a wonderful idea.
Okay, thanks for that. Andrew Lung has a question here. Maybe it's more of a suggestion, I think, maybe, but I think the question is, have you considered reaching out to the Yukon and Northwest Territory governments to establish data sharing agreements? He must be familiar because he says they have a lot of road network weather stations that cover maybe some of the gaps that you'd identified in the north.
So this is all ongoing, and this is a nice thing about the community here coming together more. So our network data scientist runs a little community of practice actually with the people involved in generating the territorial and federal databases. And so we are working on open data, open interoperability, and so on. And in some ways, it's even weird to think about that different jurisdictions in Canada need to invent and implement and operate independently the methods and infrastructure to host and distribute permafrost data, right? I mean, we might make a lot of economy of scale there if we were to not need to reinvent the wheel separately in each jurisdiction.
A lot of synergies could be found, and maybe that's something that the network idea could be bringing forward.
And are actually being found. It's just something that's not happening overnight, but I think we're well on the way to making progress there.
That's encouraging. I have a question from John Stone. So he's asking, the technologies and expertise to adapt to climate change is often in the heads and the notebooks of engineers, and not in academic journals. So his question is then hence not available then to the IPCC assessments. Is this a problem?
It would be very difficult to answer this with no, the way it was phrased. And of course that's true. And maybe we can think about this thought of networking the community better and this thought of co-development, pointing to permafrost climate services or services in general as what could be like a boundary object, the thing that we all collaborate around together, right? Once the collaboration becomes concrete, once we know what we exchange our thoughts about, it often is a lot easier. So I think, yes, it's a problem. I think especially in permafrost, there's a very good tradition of linking engineers and scientists, because a lot of the knowledge about what's in the ground rests with geotechnical engineers in large projects, because they have the money to actually do the drilling and the construction. There's a long tradition for this link.
Right. Okay, I think Barry's back. He's got a question here. Having worked at WMO, have you had any discussion with WMO on your thoughts about permafrost climate services?
I haven't so far, but I would be delighted to have them. I'm sitting on a little draft for a paper outlining some of these ideas, basically for the scientific community.
I have a question for you as I wait if anyone else wants to pop one in the chat room. You were talking about how permafrost is something that shouldn't be taking Northerners by surprise. I think it's a known challenge to deal with. And I'm also thinking about the incident that happened in Iqaluit, where the fuel seems to have got into their water supply. And if I have my understanding correct, it was an issue. They're thinking the permafrost is melting and the holding tanks are shifting. And so I guess a couple of questions sort of in regard to that. Is that something that maybe they should have seen coming? Is that something that, when working with stakeholders, can the municipal infrastructure folks be involved and aware? Just a couple of questions around that. Is that something that I think is going to be seen more and more?
So I think it's going to be seen more and more, right? Because the assumption behind many of the constructions we have in the north, and this could also be, drill sumps or impoundments for all kinds of things that rely on frozen core dams, right, that are thawing. So the assumptions are no longer valid, right? The assumption of stable climate, and the problems are going to multiply. I would be extremely careful to say, the municipal managers should have seen that coming, because I think this comes back to this SROCC finding, right? The vulnerable people often don't have the capacity to adapt. I think they would have seen this coming probably if they had the capacity. I mean, people are so thinly spread in the north to dealing with this. And, days have a finite amount of hours. And the other interesting thing is that when you look into the educational backgrounds of people in territorial governments and so on, you probably in the Northwest Territories, at least, hearsay tells me that there must be 50 or 100 people in the government that have water in their title. But until recently, there was one that had permafrost in his title. And again, this I think speaks maybe to an urgent need to develop capacity that is, broad and able to react nimbly.
Yeah, thanks for that response. Maybe we'll just take this as the last question because we're coming up to 1 o'clock. David Fisher, again, has a question about what are the prospects for remote sensing of excess ice content as a function of depth?
Thanks, David. This is so, to my understanding, there's really there's really only one method that sees ice, and that's if you look at the dielectric response in the low, in the low kilohertz range. And so there is a method that I'm playing with in my lab that's called spectral-induced polarization. It's a little bit like electrical resistivity tomography, where you can, from the ground surface down, detect permafrost, but it's pretty experimental and difficult. The other thing is airborne electromagnetics that have been processed to give at least a hint of the amount of ice content in the soil. It's difficult to say how much of that is excess ice that would have to be estimated. And there are a few things that might give us some progress. It's very difficult and very, very expensive.
Okay, I think with that, then maybe we'll wrap up. It's my honor to be able to thank you, Stephan, for joining the CMOS Ottawa Centre virtual luncheons that we're having here. A great presentation, a really great overview of permafrost in Canada, from the measurements and the observations through to the modeling, through to working with stakeholders, and this idea of climate services is great. It's lovely to see the network moving forward. I'd mentioned before the call started, Stephan was part of a CMOS Arctic Special Interest Group session that was held at the ArcticNet annual science meeting last December. And it's obvious that despite the pandemic, work has been moving forward. So kudos for you on that. But again, on behalf of the entire center, thank you very much for joining us today, and stay safe.
Well, and thank you very much for having me. It's been a pleasure. Have a nice day, everyone.
Okay. And I'm just going to take a moment to encourage everyone who's joined us today to please come back again. We have these regular monthly presentations. Now we're taking December off as a bit of a vacation month. It's a busy season for everyone. So our next session is going to be on the third Thursday in January, so it'll be January the 20th. We're having two students to co-present together on their research work. Their names are Trevor Anderson and Astrid, I think it's Schetzlar, will be speaking on their research work. So we look forward to hearing from that. Any last words from you, Barry?
Nope. Just hope everybody, since we won't have a December meeting, then wish everybody a holiday season and stay safe. And we'll see you in the new year.
Okay, thanks again, everyone. Yes, stay safe, stay strong, and we'll see you in 2022. Take care.